くりレ夢ムです。
ゆっくりマリサだぜ。
Hi, Raimo. Hi, Marissa. Hey guys. Let's learn about Schrödinger's cat.
ゆっくりしていってね。
There is a thought experiment so famous that its name has escaped the physics lecture hall and worked its way into everyday language. People use it to describe relationships, career decisions, test results, unopened emails. It's like Schrödinger's cat, meaning something that could go either way, whose outcome you haven't yet faced. Chapter 8. Pilot Wave Theory. The deterministic alternative. One of the most remarkable facts about quantum mechanics is this. Louis de Broglie, one of the founders of wave-particle duality, proposed a completely different framework in 1927, a framework that preserves determinism, gives particles definite positions at all times, and reproduces every prediction of standard quantum mechanics without any wave function collapse. De Broglie called it pilot wave theory. It was later developed more fully by David Bohm in 1952 and is sometimes called the de Broglie-Bohm theory or Bohmian mechanics. The idea is as follows. Particles are real, and they have definite positions at all times. But they are not alone. They are accompanied by a wave, described by the Schrödinger equation, that propagates through space and guides them. The wave goes through both slits in the double-slit experiment, producing an interference pattern. This is deeply satisfying from a philosophical standpoint. Einstein would have loved it. Reality is real whether observed or not. The moon is there even if no one looks. The cost is non-locality. In Bohmian mechanics, the wave that guides a particle can extend across any distance, and what happens to a particle in one place can instantly affect the wave, and thus the guidance, anywhere else. The theory is explicitly non-local. This bothered Bohm and continues to bother some physicists. And here is the deepest problem for de Broglie-Bohm theory. In 1964, physicist John Bell derived a mathematical inequality that any local hidden variable theory must satisfy. Experiments by Alain Aspect in 1981, and since refined and repeated many times, showed that nature violates Bell's inequality. This proved that no local hidden variable theory can reproduce all the predictions of quantum mechanics. Bohmian mechanics survives this test only because it is explicitly non-local, but that non-locality cannot be used to send signals faster than light, so it doesn't violate relativity in any practical way. Whether it is a feature or a flaw depends heavily on one's philosophical preferences. Chapter 9. Decoherence. The environment as the decider. In the 1970s and 1980s, a new approach emerged that many physicists believe resolves, or at least dissolves, the practical aspects of the measurement problem without committing to any particular interpretation. This is the theory of quantum decoherence, developed most completely by physicist Wojciech Zurek. These interactions entangle the system with its environment at an extraordinarily rapid rate. And once a system is entangled with an environment containing an astronomical number of degrees of freedom, the interference effects, the quantum correlations that make superposition observable, become essentially impossible to detect. The superposition doesn't disappear, but it spreads out into the environment so thoroughly, becomes entangled with so many environmental degrees of freedom, that no experiment you could ever perform would reveal the interference. From any practical standpoint, the system behaves as if it has a definite classical state. Zurek pointed out that a macroscopic object like a cat is constantly radiating photons, interacting with air molecules, exchanging heat with its surroundings. The decoherence time, the time it takes for quantum coherence to be destroyed by environmental interactions, for a macroscopic object is not just short. It is incomprehensibly short. For an object the size of a dust particle, the decoherence time is far shorter than the Planck time, the smallest meaningful unit of time in physics. For a cat, the decoherence time is so vanishingly small that even in principle, even in theory, no measurement could reveal the cat in a genuine quantum superposition. As Zurek wryly noted, a real cat would never stay in a coherent superposition of alive and dead, not even for a microsecond, because all the particles that make up a cat constantly shed information about their state into the surrounding environment. The only way to prevent decoherence would be to isolate the cat completely, sealed off from all electromagnetic radiation, cooled to near absolute zero to stop thermal processes, shielded from all gravitational effects. At which point, keeping the cat alive would be the least of your problems. Decoherence elegantly explains why we never see cats in superpositions, why the macroscopic world appears classical, and why the specific states that survive environmental interaction, the so-called pointer states, correspond to the classical properties we actually observe. It explains the boundary between the quantum and classical worlds as a matter of degree rather than kind. As you scale up from electron to atom to molecule to dust particle to cat, decoherence happens faster and faster until it is effectively instantaneous. What decoherence does not do is choose. It explains why we cannot observe the interference between the alive cat and dead cat branches. But in the many-worlds language, both branches still exist. Decoherence explains why we never see them interfere. It does not explain why we end up in one of them. The measurement problem, in its deepest form, survives decoherence. Chapter 10, Wigner's Friend. The problem gets personal. The measurement problem does not just apply to cats. It applies to people. Eugene Wigner, a physicist who won the Nobel Prize in 1963, proposed a disturbing extension of Schrödinger's scenario. Imagine a physicist, call her Wigner's friend, who is inside the laboratory, watching the cat. From her perspective, when she opens the box, the wave function collapses and she sees either a live cat or a dead cat. Her measurement is complete. The cat has a definite state. But now consider Wigner himself, who is outside the sealed laboratory, with no information about what happened inside. From his perspective, the entire laboratory, including his friend, the box, the cat, the measuring apparatus, and all the air molecules that interacted with all of them, is a quantum system. Until he opens the laboratory door, everything inside, including his friend's brain and her memory of what she saw, is in a superposition. From the friend's perspective, the cat has a definite state. From Wigner's perspective, the friend herself is in superposition. Is she in a state of having seen a live cat, or in a state of having seen a dead cat? Both descriptions are formally correct in standard quantum mechanics, applied to different systems. But they cannot both be objectively true at the same time. Or can they? This is not a thought experiment about measurement instruments. It is a thought experiment about the consistency of observers. Can two observers have genuinely different, irreconcilable accounts of reality at the same time? And if so, what does this say about the nature of reality itself? In recent years, Wigner's friend has evolved from a philosophical puzzle into an active area of experimental research. Some physicists argue that it shows quantum mechanics must be revised. Others argue that it shows no single observer can have a God's eye view of all quantum events, that reality is fundamentally perspectival. The Cubist school, short for quantum visionism, argues that the wave function is not a description of the world at all, but a description of an agent's beliefs about the world, updated by experience. On this view, there is no paradox. Different observers simply have different beliefs based on different experiences, and quantum mechanics is the correct tool for updating those beliefs. Pause and ask. The second question, I want to stop here again and ask you something. We've now seen 4 serious interpretations of quantum mechanics: Copenhagen, many worlds, pilot wave, and cubism, plus the decoherence framework, which modifies all of them. Each interpretation makes the same experimental predictions. Each has genuine strengths. Each has genuine weaknesses. None has been definitively ruled out. If you had to choose right now, if a physicist put you on the spot and said, which interpretation do you think is most likely correct, which would you pick? Is it Copenhagen, where reality is fundamentally about knowledge and observation, and the question of what happens between measurements is unanswerable? Is it many worlds, where every possibility actually happens in a branching multiverse? Is it pilot wave theory, where particles follow definite paths guided by an invisible wave? Or is it something else entirely, something we haven't thought of yet? Tell me in the comments. And tell me why. Chapter 11, Bell's Theorem and the End of Hidden Variables. Whatever interpretation you favor, there is one result that constrains all of them. Bell's Theorem, published in 1964 by physicist John Bell, and the experiments that followed. John Bell was an Irish physicist working at CERN who was dissatisfied with the Copenhagen interpretation's refusal to ask about the underlying reality. Bell proved a theorem that any theory with the following properties must satisfy a certain constraint on its predictions. First, particles have definite hidden properties that determine measurement outcomes. Second, the measurement in one location cannot instantly influence results in a distant location. He derived an inequality, a bound on the correlation between measurements on entangled particles, that any such theory must satisfy. Then he showed that quantum mechanics predicts violations of this inequality. The experiments were done, first by a Lan aspect in Paris in 1981, and subsequently by many others with ever-increasing precision and ever-closing loopholes. The most definitive tests, including the 2015 loophole-free experiments in Delft and Vienna, showed unambiguous violations of Bell's inequality, exactly as quantum mechanics predicts. The conclusion is inescapable. Nature is not locally real. One of Einstein's two foundational assumptions, either that particles have definite pre-existing properties or that measurements cannot instantly affect distant locations, must be abandoned. Pilot wave theory survives by abandoning locality. Copenhagen survives by abandoning realism. The cat does not have a definite state before measurement. Many worlds survives by abandoning the idea that any single outcome actually occurs. Bell's theorem did not solve the measurement problem, but it proved that whatever the solution is, it cannot preserve both locality and realism simultaneously. The world is strange at its foundation in a way that cannot be escaped. Chapter 12. The quantum world made real. Technology that lives in superposition. While philosophers and physicists argue about what quantum mechanics means, engineers have gone ahead and built devices that exploit the quantum phenomena at the heart of Schrödinger's cat. Quantum computers are perhaps the most striking example. A classical computer processes information in bits. Each bit is either a 0 or a 1. A quantum computer uses quantum bits or qubits, which can be in a superposition of 0 and 1 simultaneously. A system of 10 qubits in superposition can represent all 1,024 possible combinations of 10 bits at once. A system of 300 qubits in superposition can represent more states simultaneously than there are atoms in the observable universe. When a quantum computation is performed, it exploits the interference between different computational paths, exactly the interference that lies at the heart of the double-slit experiment and Schrödinger's cat, to find answers that would take classical computers astronomical amounts of time to reach. But here is the connection to our story. Superposition is fragile. The moment a qubit interacts with its environment, the moment any information about its state leaks out, decoherence destroys the superposition, and the quantum computer becomes a very expensive classical computer. Building a functional quantum computer is, in essence, the challenge of keeping Schrödinger's cat alive for long enough to be useful. The engineers call this maintaining coherence, and it is the central engineering challenge of quantum computing. Every qubit is a tiny Schrödinger's cat. Every quantum computation is a race against decoherence. And every breakthrough in quantum error correction is a step toward controlling the very processes that Schrödinger's thought experiment put on the table in 1935. The strange quantum world that seemed so abstract, so philosophical, so removed from everyday reality. It is now being harnessed in laboratories to do computation, communication, and sensing that classical physics cannot achieve. And at every step, the questions Schrödinger raised in 1935 about superposition, measurement, and the boundary between quantum and classical are not philosophical background noise. They are engineering constraints. Chapter 13. What is observation? What is reality? Let us come to the deepest level. The measurement problem is ultimately not a technical problem. It is a philosophical one. It asks, what is the relationship between physics and experience? Between the mathematical structure of quantum mechanics and the felt quality of lived reality? Consider what quantum mechanics actually says, at its most basic level. It says that the world is described by a wave function, a mathematical object that encodes probabilities for all possible outcomes of all possible measurements. It says that when a measurement is performed, a definite outcome is obtained, with probabilities given by the wave function. It says nothing, at least in its standard formulation, about why a definite outcome occurs, or what it means for a measurement to take place, or who or what counts as an observer. The question, what is an observer, sounds like it should have an obvious answer. a person, a detector, a machine. But when you try to be precise, the question becomes treacherous. Is a thermostat an observer? It registers temperature. Is a camera an observer? It registers light. Is a human brain an observer? At what point in the neural processing chain does observation happen? Some physicists, most notably John von Neumann and later Eugene Wigner, concluded that consciousness must play a special role, that the collapse of the wave function requires a conscious observer to be triggered. This view has mostly fallen out of favor in the mainstream, not because it's been definitively disproved, but because it seems to introduce more problems than it solves. It makes the collapse of the wave function depend on a concept, consciousness, that is itself one of the most poorly understood phenomena in science. Cubism avoids this problem by not requiring collapse at all. In the cubist picture, the wave function is personal. It belongs to an agent, not to the world. Updating the wave function upon receiving an outcome is not a physical process. It is a cognitive one, the agent's rational updating of beliefs. Different agents have different wave functions, and there is no contradiction because the wave function was never supposed to describe the world in the first place. Relational quantum mechanics, proposed by Carlo Rovelli in 1996, takes a similar perspectival approach. It says that quantum states are not absolute. They are defined relative to a system. The cat is in superposition relative to Wigner. The cat is in a definite state relative to Wigner's friend. Both descriptions are correct, relative to their respective reference systems. There is no God's-eye view of quantum reality that is true for all observers simultaneously. What these interpretations converge on, what seems increasingly hard to avoid, is the conclusion that quantum mechanics does not describe an observer-independent reality in the way classical physics did. It describes a web of relationships between systems, between agents and the world, between events. Whether this means reality is fundamentally relational, or fundamentally probabilistic, or fundamentally many-branched, or fundamentally guided, we do not know. The equations cannot tell us. Chapter 14. What Schrödinger actually believed here is the final irony in this story. Schrödinger spent decades working toward his own interpretation of quantum mechanics. He was deeply influenced by Hindu philosophy, particularly the Vedantic concept of Brahman, the idea that consciousness is not something individual minds generate, but a single underlying awareness in which all experience occurs. His book, What is Life?, published in 1944, profoundly influenced the founders of molecular biology. It was one of the books that inspired Francis Crick and James Watson in their search for the structure of DNA. And in his later philosophical writings, Schrödinger argued for a view that might be called panpsychism or idealism, that the material world described by physics is a representation in consciousness, and that the apparent plurality of observers is an illusion. There is, in the deepest sense, only one mind. This is, to put it mildly, a minority position among physicists, but it is not incoherent, and it resolves the measurement problem in a certain way. If what we call the collapse of the wave function is really the entry of an event into a singular unified consciousness, then there is no paradox about who observes what or when. Schrödinger's cat, then, was not just a philosophical puzzle. It was a window into one of the deepest questions a human being can ask. What is the relationship between the observed world and the observing mind? Between physics and experience? Between matter and meaning? He did not create the cat to illustrate quantum weirdness. He created it to ask whether quantum mechanics, taken seriously, forces us to revise our most basic ideas about what it means to exist, to know, and to be real. 90 years later, that question is still alive, still open, still, in the deepest sense, unanswered. Epilogue. The cat is still in the box today. We traveled from the origins of quantum mechanics in the early 20th century, through Schrödinger's wave equation and his growing unease with the Copenhagen interpretation, through the original 1935 thought experiment and the philosophical crisis it exposed. We examined the Copenhagen interpretation and its pragmatic refusal to answer questions about unseen reality. We explored Everett's many worlds, with its branching multiverse and unresolved probability puzzle. We looked at pilot wave theory, with its determinism and inescapable non-locality. We understood how decoherence explains the appearance of the classical world without solving the measurement problem at its deepest level. We met Wigner's friend and the disturbing implication that observers can have irreconcilable accounts of reality. We absorbed Bell's theorem and its proof that the world cannot be both local and real. And we looked ahead to quantum computers, technologies that live, breathe, and die by their ability to maintain the very superpositions that Schrödinger considered absurd. What I want to leave you with is this. Schrödinger's cat is not a cute metaphor. It is not a story about uncertainty. It is a precisely posed challenge to the deepest assumptions we make about the nature of physical reality, about what it means for something to be real, to be definite, to exist. The cat is still in the box. The interpretation of quantum mechanics is still unsettled. Some of the greatest minds in physics today, David Deutsch, Sean Carroll, Roger Penrose, Carlo Rovelli, Alain Aspect, Anton Zeilinger, hold deeply incompatible views about what quantum mechanics is telling us about the world. They all agree on the predictions. They disagree, profoundly and without obvious resolution, about the meaning. And I think this is worth sitting with. In an age when it sometimes seems like science has answers to everything, here is the most successful physical theory in history, a theory whose predictions have been tested to more decimal places than any other, and we still cannot agree on what it means. We still cannot say what actually happens when a measurement is made, where exactly the quantum ends and the classical begins, or whether the universe branches or collapses or simply is. Schrödinger created his cat as an argument. 9 decades later, the argument is still going, and the cat, alive, dead, or something stranger than either, is still waiting in the box. Thank you so much for spending this time with me today. If this video meant something to you, a like and a subscription help this channel reach more people who want to go deep. And I'll see you next time. The box is still closed. Thank you for spending this time with me. If this video meant something to you, a like and a subscription help more people find their way here. And I'll see you next time. The infinite is closer than you think. Goodbye, goodbye, goodbye.